I want to welcome everybody to our webinar on a sensitive topic of image performance, an EMVA technical webinar. This webinar will focus on some of the technical aspects of the EMVA. We are joined by Matt Vayner, who is our field application engineer for the machine vision cameras, and Stephen Hofmann, who is an R&D engineer managing the electro-optical aspects of the Phantom cameras, and he also manages measuring the EMVA specifications. I will record this webinar. If you have any questions, please save them to the end. I will record those into the session as well. I want to mention too that we do plan to have another webinar early next year that will be focused on some of the key EMVA specifications and how they're relevant to diverse imaging applications, specifically things like data accuracy and precision in applications like DIC, PIV tracking, and etc. Without further ado, I'm going to hand it over to my colleagues, Matthew and Stephen. Enjoy.
Thank you for the introduction, Kyle. So let us begin. Everybody can see so switching the slide right there, everybody can see. So we'll start off with an analogy. When you compare two cameras, let's say you don't really know much about what's good, but you know that you have light, it comes in, it enters a black box. Let's say this is camera A, and it outputs an image. And the image, of course, is just an array of pixel values. And your computer knows to interpret these pixel values as color, or rather just a mono gray value, a digital count. So the higher these pixel values, the brighter that pixel is going to be. Now you have another camera, light in, it goes into the black box, and an image comes out, and it looks like this with these pixel values. So if your light is all the same and you use the same illuminance, everything aperture, everything's the same, then you would determine camera A is more sensitive, right? After all, the image is brighter. Well, let's look under the hood. Let's open up the black box. You have light in, it's incident on your sensor, it hits the pixel. It generates an electron. In this case, it generates an electron. It moves down into the well, and it joins all the electrons that are sitting in your well there. This is called the ADC. That's your analog to digital converter. It detects how many electrons are in your well. And here, because the well is at full capacity, whoa, this must be super bright. So it displays this as white color. And that's camera A. Now for camera B, what's going on under the hood? For the same 3 photons incident on your pixel, it generates 2 electrons. These electrons move down into the well, and you'll see here that the well is not at saturation. It's not at full capacity. So your analog to digital converter, your ADC, measures this as 170, a gray value. So not dark, but not completely saturated. So comparing these two sensors, camera A has a lower photon to electron conversion with a shallow well, and camera B has a higher photon to electron conversion and a deep well. So I think when you actually look under the hood and compare these sensors, clearly one camera is better than the other, and it's camera B. Camera B is certainly more sensitive. Even if the pixel values are darker, that is a display thing. That is just the image is displayed, is not a sensitivity thing. Digital cameras are not a direct measure of sensitivity. So what should we use instead? To us, there are 3 quantities that you should be looking out for when you want to measure sensitivity. There's quantum efficiency, there's temporal dark noise, and there's pixel area. And we'll go through each of these one by one. So we start off with quantum efficiency. So quantum efficiency is the fraction of photons which are converted into electrons. Quantitatively, it looks like this. So it's the accumulative charge over exposure time divided by the photons incident on the sensor over that exposure time. So let's look at camera B and camera A sensors again. So on the left, we have camera B sensor. So 3 photons strike the pixel and it generates 2 electrons. So that's 2 over 3 or 0.67 quantum efficiency. For camera A, only 1 electron is generated. per 3 photons. So that's a quantum efficiency of 0.33. Next, we have temporal dark noise. So temporal dark noise is the electronic, as in number of electrons, output of the sensor in the absence of light. So you'll see here on the pixel, there's no light incident on it, but electron still manages to escape through. It populates the well, and the ADC reads that as a valid gray value. Move on to system gain. So this is how you get from counts to electrons. This is necessary to evaluate important values about sensitivity. When you're looking at the EMVA spec sheet, I wouldn't necessarily use system gain to evaluate sensitivity in an intuitive manner, but it is necessary to evaluate stuff like quantum efficiency and temporal dark noise. So in this case, system gain is the number of digital counts the ADC reads per electron, and quantitatively, it looks like this. It's your digital count value divided by the accumulated charge over the exposure time plus your dark noise. Basically, if you add one more electron to the well, how many digital counts does the pixel increase by? So here you have a well with a certain capacity, and the electrons populate up to this level. Your ADC measures 140. If you add 3 more electrons, then the count increases by 1, so your system gain is 1/3. Now, a warning about system gain, and this is why we wouldn't recommend using it as an intuitive way to understand sensitivity. Because it's pretty easy to think that you'd want the camera with the best gain possible. After all, you'd be accounting for every single electron. Well, consider the following. So let's say you have a camera, there's no light incident on your sensor, so this is just your dark noise again. But now if you add 3 electrons, that's entirely just from dark noise, that increases your pixel value, and thus you get a noisier image. So sensitivity here increases, but so does noise. So that's why we wouldn't recommend using system gain to really analyze sensitivity, but system gain is featured very prominently on the spec sheet because it is necessary to calculate the values that we do recommend you use for sensitivity. Every single EMVA spec, EMVA 1288 spec, can be derived from these. Now I'll pass it over to Stephen, and he'll describe a little bit about what we do to measure these quantities.
Thank you, Matthew. So now we're going to talk about how to actually perform these measurements. So all you really need is a consistent and well-calibrated light source. In our case, VRI uses the AON ACC 2-camera calibrator model. It looks something like this. It is EMVA 1288 approved hardware. It uses 3 different LEDs for the test: a blue LED with a center wavelength at 466 nanometers, a green LED with a center wavelength of 532 nanometers, and a red LED with a center wavelength of 629 nanometers, all of which can be current controlled to adjust the brightness for the different measurements from dark to saturation. It also has an F-mount connector for easy camera connection, and it's about 90 centimeters long, 13 centimeters wide, and 14 centimeters high if you're interested in that. So now to actually talk about some of these measurements and deriving them. So unfortunately, we're not able to see the electrons, and we don't have a way to probe them directly. So we want to run a couple different tests to derive 3 quantities: quantum efficiency, system gain, and the temporal dark noise. So looking at the first test is the characteristic curve. Now, this is not actually reported on the EMVA 1288 summary sheet, but it's really important to derive these specs. So we want to see how the digital counts change with the number of incident photons. And you may be thinking, isn't this just a black box all over again? Well, yes, but we can take a look at this a little bit more carefully with a plot. So here we have some actual data from one of our cameras, the T4040, and we can see when plotting the incident photon pixel average on the x-axis and the digital counts on the y-axis, we have a linear relationship. And we want to know, is this slope of the characteristic curve? Well, as it turns out, the slope is actually just the product of the quantum efficiency and the system gain. And we can actually convince ourselves this is true by looking at the units. We know that quantum efficiency is in fact the conversion factor from photons to electrons, and we know K, the system gain, is the conversion factor for electrons to counts. So looking at this here, we see counts per electron times electrons per photon. The electrons cancel, and we're just left with counts per photon, which is exactly the conversion factor that we need to map the light into counts. So we have now determined that the slope of the characteristic curve is the quantum efficiency times the system gain. So we still have two unknowns and one equation. Therefore, we need one more equation to be able to figure out what these unknowns are. And I'm back to Matt now to continue on.
Thank you, Steve. So the next test, we need to look a little bit past just average values alone. So how confident can you be that a single frame presents the correct response to light? How consistent are your shots frame to frame? And this might be a little abstract, so I prepared some examples. So which camera would you prefer? Would you prefer the one on the left or the one on the right? So the one on the left has a low variance, that there is very little variance from frame to frame between the pixel values. They're generally around the same gray value. That is not the case for the camera on the right. The camera on the right, the pixel values are changing a lot compared to the average gray value. So this is called variance. And I think now quantitatively what we do for the measurement is, well, let's say you look at a single pixel, and this is a graph for frequency is just the amount of times you see this pixel value. So in this case, for the first frame, we see the pixel value of 100. So we mark that, and now we have a frequency of 1. And we keep running this measurement. Next time we get 99 and 98. Oh, we get 100 again. So now the frequency is 2, and so on, and so on, and so on. And eventually we'll get a populated chart like this, where the average value is 100, but there's still a little bit of variance, a little bit of spread from that ideal 100 value. And this is pretty good. So this is a very low variance camera. Next, for perhaps other sensors, you'll get a plot that could look like this. And if you would believe it, the average value is still 100, but there's a wide variance of gray values. So that's why we need to look at consistency and not just the average digital counts. So variance is a measure of consistency, and we call that sigma squared, DC for digital counts. Here, just as an example for the what a variance could look like in terms of probability. So you have a very narrow variance for the blue camera, a very wide variance for the green camera. And all cameras have the same mean, but from frame to frame, you'll find that the orange and green cameras have way more variance. They're not very consistent. So which camera would you prefer? If you compare the variance to the mean values, the average values of the digital counts, we can effectively see how consistent our camera is to changes in light conditions. And that's just as Steve mentioned with the characteristic curve, because we can relate digital counts to light. So we see how consistent our camera is to changes in light conditions. And this is called the photon transfer curve, and it is featured on the EMVA 12E8 spec sheet. And it looks like this. And again, so everything we have here is also real data from the T4040 camera. And you'll see here that the variance dependent on the digital count. So effectively, you're looking at how consistent your camera is over variations in light conditions. But it's okay. Maybe it's this a little. It's not very intuitive. Like, what do you do with this data, and why is it on the spec sheet? So you can make a reasonable assumption that the slope of that graph is the system gain K, which is why it's the system gain is important. It's like, well, you might say, huh? Well, so consider this, and this is the argument, or plausibility argument. The total variance of the digital counts is entirely dependent on the variance of the electronic noise. So here, the variance in the digital counts is proportional to the electronic noise, and that symbol just means proportional to. And electronic noise has a very special property that its variance is equal to its mean. And this is a property of electrons as particles. The technical term, it's a Poissonian distribution. And for this particular type of statistics, the variance is equal to the mean. So the average number of electrons that's coming through is equal to the variance of that statistical distribution. But we know from the conversion factor that we know the conversion factor from electrons to counts. That's just K, the system gain. So the average electrons coming through is equal to K times the average digital counts. And thus, the variance in the digital counts is proportional to the system gain times the average of the digital counts, where here we just replaced the average electrons coming through with the variance on those electrons coming through. And it turns out that the slope is actually not just proportional to, but it is exactly the system gain. So the slope of this graph of the variance of the digital counts with respect to the average of the digital counts is just the system gain. Now here's the full quantitative equation, just for completeness. You subtract off the digital dark counts here, and this term here is called the offset. So you'll notice in the previous graph that it doesn't start exactly at 0 on the y-axis. There's a little bit of an offset. And it turns out this is what that offset is. So the value is the offset of the line when the average of the counts is closest to 0. And that's the dark noise itself. So just like with the electron variance, the analog dark noise also has the special property that the variance is equal to the average of the dark counts. And thus, the average of the dark counts is equal to your offset of that graph divided by K squared. Actually, a little bit of a nuance here. You actually have to subtract by 1 over 12. This is called the quantization noise. And it's outside of the scope of this discussion. We're happy to provide more information, but just for completeness here, no, there is a 1/12 factor there. It's called the quantization noise, and it's just 1 over 12. So graphically, it looks like this, where the offset is equal to this term plus 1 over 12. Let's sum everything up. We measured the digital counts as a function of the incoming light, and we measured the variance of those digital counts as a function of the average digital counts. And then we use those to evaluate the system gain, which is just the slope of the photon transfer curve. We evaluated the quantum efficiency, which is the slope of the characteristic curve divided by the system gain. And we evaluated the temporal dark noise, which is the offset of the photon transfer curve minus that 1/12 factor divided by the system gain squared. So this is why we introduced the system gain, where we need the system gain in order to evaluate quantum efficiency and temporal dark noise, which are absolutely crucial to understanding sensitivity of digital cameras. So moving along, there's some other important quantities in the EMVA 1288 spec sheet. The first one is signal to noise ratio, or SNR. The signal to noise ratio is exactly as it sounds. It's the ratio of the signal to the noise. The higher the noise, the lower the SNR, and vice versa. Graphically, it looks like this. So there's a sinusoidal signal on the left, and it's very noisy, so very low SNR. And there's a sinusoidal signal on the right, which is not very noisy, so a very high SNR. And you can make out the original sinusoidal signal very easily on the right side, but perhaps not very easily on the left side. So the definition of these measured quantities, it's the SNR is the average of the digital counts minus the dark counts divided by the standard deviation of the digital counts. Note that that is not squared. So it is not the variance, it is the standard deviation. That's why you saw the sigma squareds before with the variance. So here, this is called the standard deviation. And we plot the SNR as a function of the photons per pixel average using this equation. So here, this is what you're going to see on the EMVA spec sheet. It's a lot to take in, so we'll go through it step by step. First of all, you might notice that the axes look rather interesting, and that's because this is a log-log plot. So both the x and y axes are plotted on a logarithmic scale. Perhaps you're more used to plots where the axes are linear, so you go from 0, 1, 2, 3, and everything is evenly spaced. But here, it is evenly spaced exponentially, so you have 10 to the 1, then 10 squared, then 10 to the 10 cubed, 10 to the 4th, and the same on the y-axis. Next, we see that the data in pink, this represents the SNR at a particular amount of light incident on the pixel. The threshold needed to determine signal from noise is when the SNR equals 1, and that is the absolute sensitivity threshold, AST, and that's shown on the left. The saturation threshold, when the well is full of electrons and cannot accept anymore, is shown to the right. And then the theoretical maximum is the highest physically possible SNR as determined by shot noise. So you can imagine that if you have literally zero read noise, no electronic noise whatsoever in your system, you are still limited by the fundamental quantum nature of light, and you are going to have shot noise. And that is entirely dependent on just your illumination conditions. Why does SNR matter? Maybe this was a little abstract, a little mathematical. Well, here's exactly why it matters. If you remember the equation, on the left side, we have a noise field where the standard deviation doesn't really change that much from the black background. So you are able to determine that square signal traversing from the top left to the bottom right of the field. But on the right side, the standard deviation, it deviates very strongly from the black background. So you can't really determine that same signal traversing from the top left to the bottom right of the field. That's why SNR is important, and that's why you want to aim for the best possible SNR you can get. Next up, we have dynamic range. So dynamic range is the ratio of the saturation threshold to the absolute sensitivity threshold. So remember, saturation is where the well is completely full and it cannot accept any more electrons. The absolute sensitivity threshold is when SNR is 1, when you can actually determine signal from noise. And this takes on the usual meaning for dynamic range. So higher dynamic range means a sensor can capture details in both shadows and highlights. Low dynamic range means shadow and highlights either get under or overexposed respectively. So effectively, this is like windowing in to fewer pixel values at a certain exposure. If you have a low dynamic range, you'll have to choose which features you'd like to view. So graphically, that would look like this. The animation is a little off sync. So we start here. We have very high dynamic range. It starts shrinking. So now the gray values you have access to at a certain exposure value, that really narrows in what you can view without over or underexposing your image. So again, right now the GIF is so very narrow gray values and restarts, and we have a very wide range of gray values. So we can get a lot of pixel values imaged with a single and certain exposure. All right, and I'll pass it back to Stephen again to talk about spectral response and how we measure that.
Thank you, Matthew. So spectral response is very important. When looking at the EMVA 1288 data sheet, we see that we get a quantum efficiency value, but this is at a particular wavelength. For mono, it's just using the green wavelength. Color, we get one for each color channel, but we want to see how this may vary across the entire spectrum. So we use an additional test at VRI to determine, to measure how the camera responds per wavelength of light. So when we do this, we also consider the pixel area in this measurement. And to actually run the test, we first have to measure the optical power per wavelength using a power meter, and this will give us across the spectrum a value in watts. We then will measure the camera's response in digital counts, again, across the entire wavelength spectrum. Because we know the system gain of the camera, we can then convert the digital counts into electrons. And then we're able to calculate the current because we know the number of electrons that are flowing through the camera, and this will be reported in amps. So our response then is just amps per watt. So now to determine what the quantum efficiency with the fill factor is across the entire spectrum, we can use this formula here, 1240 times the response divided by the wavelength, where 1240 is just a conversion factor for the wavelength of a photon to the energy of a photon. So we can do some unit analysis to convince ourselves that this is how we can get the quantum efficiency. So we have that it's the energy times the wavelength divided of a photon. We know that the response we had measured in amps per watt, and we still have the 1 over wavelength. We see that the wavelengths cancel, And then if we continue further, we know that amps is electrons per second and watts is energy per second. We can get a few more units to cancel here. And we see that, we're left with just electrons per photon, which we know is in fact the quantum efficiency. And I'm going to hand it back to Matt for a few additional parameters that are reported on the EMVA spec sheet.
All right, thank you, Stephen. Okay, so now just finishing up here with other parameters that aren't as paramount as quantum efficiency, temporal dark noise, and the pixel area. So on the EMVA spec sheet, you also see stuff like spatial non-uniformities. You have, so these are just the variations in pixel response across the image sensor under uniform illumination. You have linearity errors, so that's deviation from linearity of the photon transfer curve. You have your dark current, and this is not temporal dark noise. That's why it's very important in this this presentation, this webinar. We are calling it temporal dark noise. Dark current reported is not that, and it is the signal generated over long periods of exposure time in the absence of light. So dark noise, as defined before, the temporal dark noise, as defined before, is variations on that signal. Of course, more information about any of these parameters can be found at our website at phantomhighspeed.com. Key takeaways. So what's a good heuristic to take away from all this? What do you need to know in order to determine, is this camera more sensitive or less sensitive than a comparable camera? So first, the quantum efficiency should be as close to 100% as possible. Second, the temporal dark noise should be as close to 0 as possible. Third, sensitivity is the highest responsivity, QE and pixel area both considered in there, with the lowest temporal dark noise you can get. Fourth, the SNR should be as close to the theoretical maximum as possible. And last, dynamic range should be as high as possible. And that concludes our webinar. Thank you for attending. We will take any questions.
Yeah, so guys, please feel free to go ahead and write some questions in the chat. We already have one question, which I'm going to ask Matt to address. We had one, and ask if you can just go over the QE slide one more time. So if you could, yeah, just a brief explanation of quantum efficiency one more time.
Sure. So what happens fundamentally is light strikes the CMOS sensor. So it strikes the piece of silicon or whatever the material is, and it excites an electron. It excites an electron to be conductive, meaning it can move around freely. And the idea in the camera is that you steer that electron into the well, and then it's measured by your circuitry. So in this case, quantum efficiency is the ability for your sensor to swap light for electrons. So so in this case, we consider light to just be packets of energy, which we call photons. So here, if you have 3 photons incident on a pixel, then, well, with a perfect quantum efficiency, then each of those photons should be able to excite an electron to be conductive and to be able to move freely. But we don't live in a perfect world. There are several reasons why you can't get perfect quantum efficiency. But in this case, quantum efficiency is defined as the ratio of how many electrons you do generate to how many photons are incident on your sensor. So when we measure the spectral response, that quantum efficiency using the equations that Stephen mentioned, where instead of working with photons, you work with a general illuminance and you figure out how many photons using the conversion factor from the wavelength of the photon to the energy, and then finally to a quantum efficiency, since all of those terms cancel and you're just left with electrons per photon.
Great. Do we have any other questions about the EMVA specifications from anybody else? One question was, do you measure responsivity directly with RGB light source, or do you need a monochromator?
Oh, we use a monochromator.
Yeah. So
Yeah.
You can,
Oh.
so Stephen will answer that.
So just leaving presentation mode here, moving all the way down.
Yes, for our spectral response measurements, we do in fact use a monochromator.
Perfect. Are there existing SNR calculators that help in comparing cameras of different vendors to our sensors, essentially? So, yeah.
Unfortunately, they're not that we're aware of at this time.
Larry asked, does dark current relate to fixed pattern noise or something else?
No.
You want to maybe define a little bit what dark current is again?
Yeah, I think for any of our high-speed cameras, we're very proud to say they are quite fast. So when it comes to dark current, the exposure times that you're working with are, dark current is going to be rather negligible, which is why it's variations on that signal, which are not negligible. You do have to consider temporal dark noise, not only for our camera, but any camera that you're looking at on the market. In that regard, dark current is just something that builds up over time, but because our exposure times are so short, then it's rather negligible for choosing a high-speed camera, which is why we include it here for completeness in the other parameters, but it's not something that we would consider as paramount as temporal dark noise when it comes to measuring sensitivity.
Thanks, Matt. Another question we had as an add-on was, are there SNR calculators for different cameras and sensors? The answer to that is no, that's not a widely available thing. However, if the given sensors you are comparing have the EMVA 12888 protocol performed on it, then yes, you can do a very nice scientific comparison between the two sensors. So, that's one thing to think about. Yeah. Any other questions we have from the chat? I would like to remind everybody that probably early next year, we will have another webinar that will focus on how these specific EMVA specifications correlate to the performance in diverse applications, which will be an exciting one and probably more relevant to the diverse group here. So we appreciate everybody for logging in and listening in. We will go ahead and finish this recording, and we will share the slides and the presentation with everybody. So have a great week, and we hope to hear from you guys soon. Thanks. Bye.
Thank you, everybody.
Thank you.
Thank you.